Hello, in this video we're going to calculate the gravitational potential energy. So this is going to be any system that is an external object plus the Earth, and those together are our system. So we'll just use a ball, although this works just as well for rocks and squirrels or anything that would fall. So thanks to the Earth, there's a force of gravity acting on this object, which has magnitude mg and direction down, so we could just say negative mg. And then we'll have some positions. Let's put those in a different color. So we can have, say, y equals 0, be a position there, and then we can move the object upwards, either by, say maybe someone's lifting it up. So it ends up at some new position y that's not 0. And to keep our symbol straight, we'll call this y initial. So y initial will be 0, and then y final we'll just call y. And we're going to choose to have the initial potential energy at the initial position be equal to 0 at this point here. That's a choice we get to make, although that is almost always the choice that's made with gravitational potential energy. So that if we calculate what it's going to be, remember the formula for that would be the potential energy is equal to whatever its initial value is chosen to be, minus the integral of f times dx. In this case, let's say y. So fy times dy, and we'll go from y initial to y final. So in this particular setup, we chose to make our initial potential energy 0, and y initial was equal to 0, y final is equal to y. The force of gravity is equal to negative mg, and then we'll have a dy. So this integral is pretty straightforward because m and g are constants, and so we get the potential energy due to gravity is equal to minus minus, so plus mgy. Now it's not unusual to see this written as mgh. Just a different choice of symbols here. That way you're not reusing the coordinate y if you want to use it somewhere else in your problem. So h here would stand for height. Okay, so that's our gravitational potential energy. This will be one of the more common energy formulas you use, along with kinetic energy. Also, I want to point out that you could have a negative y coordinate. There's nothing that says that the ball couldn't end up lower than where it started, in which case the potential energy could be a negative number. That's okay. Potential energies can be negative. Remember, kinetic energy couldn't because there was no way to have a negative energy in that formula. The kinetic energy formula, as you recall, is 1/2 mv squared, and mass can't be negative. And if you square velocity, that couldn't be negative unless it was somehow imaginary. So physically, you're never going to have a negative kinetic energy, whereas you could have a negative potential energy. Also, let's compare this answer to the amount of work done by gravity and see how that compares. And again, this is the work done by gravity, not whatever force is making the ball move, but by gravity by itself. So work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between them. The magnitude of the force of gravity is mg. The magnitude of the displacement here is y minus 0, so just y. And those two vectors are in opposite directions. So this would be cosine of 180 degrees, which is negative 1. So the work done by gravity is equal to negative mgy. Okay, so the difference here is that work's got the minus sign, potential energy has the positive sign. Why might that be? Well, not such a big surprise. It's because work is equal to the opposite of the change in potential energy. You might say that's not quite consistent. This is a change in potential energy. That's just a potential energy. Yes, but we made the initial potential energy 0, so if I want to make this a change, all I have to do is subtract 0, and hey, I get the same number. Also, it's kind of neat to point out that this is a negative work, okay? So that means that this is energy removed. So where did it go? I don't want quotes just yet. I want them over here. So this lost energy is actually just going to be stored as potential energy. So you can think of potential energy as stored energy. That's what potential here means, is it could potentially do something else. It could potentially, say, become a kinetic energy because it's being stored. And how did it get stored? Well, some internal force must have done negative work to put it there. All right, so next video we'll do the potential energy for a spring. See you in a moment.